is that? What do you press?
Math and over number.
Math, new, and then is it 1?
Yeah.
All right, get that in a nice window. By the way, if we ever go too fast, raise your hand and say, Mr. Mikowski, you know, I can't keep up with you with this moving. You know what you're doing, but I got to do it on my calculator. Have you got abs? All right. Now, check this out. Zoom in on this. Every time you zoom, do you see a similar picture? Press zoom in. Zoom in. Do you see a similar picture? Right? You say, well, where are you going with this, Mr. Bukowski? I'm going here. What does that have to do with locally linear? Well, it has the following to do. New picture, kill y1 equal abs, and do y1 equals x squared. An old friend. Hush. Right. Kill y1 equals abs, do y, or you could do make this y2, but I think it's better to do another y1. Now, look at the origin. What's the tangent line at the origin? 0, the x-axis, right? Isn't that the tangent line? All right, zoom in on this, and what do you discover? If you zoom in. Doesn't the graph tend to flatten out as you get close to the origin?
Yeah.
As opposed to this? This remains obstinately pointed the whole time. It never changes. In the vicinity of the tangent line, a differentiable graph is very close to the tangent line. In other words, the graph and the tangent line are almost indistinguishable. Not only just here, but all the time. Therefore, you say functions with a derivative are locally linear. Are they ever totally flat? No. This is never not bent. It's always bent. But as you get close to that tangent point there, the bend is less and less from the tangent line. That never happens here. You say, well, why didn't it happen here? Because there's no derivative here. You say, yes, there is. And I say, well, why is that? You say, well, this is the tangent line, the x-axis just as before. And I say, why is that? And you say, well, it goes through the point. And I say, well, you know, if just going through the point where all that you had to do, and every line that goes through it's a tangent line. If that's your only criterion, right? The y-axis would be a tangent line. You say, well, why is there a derivative at the origin? Well, I say, look to the left. What's the slope? She's going down. It's supposed to be negative 1. Slope is negative 1. What's the slope to the right? Positive 1. Okay, never the twain shall meet. This is always, I don't care how close you come to 0. To the left, she's negative 1. To the right, she's positive. There is no derivative here. You say, well, that means there's no tangent line. Yeah. You've got to wake up. According to the definition, there is no tangent line to absolute value at the origin. There isn't. I don't care. There's no break. There's no hole there. There's no tangent line. Because there's no derivative there. Oh, you're mildly unencouraged here. What happens here? Tangent line is negative, less negative, less negative, less negative, going to 0. Positive or positive, less positive, less positive, smoothly going to 0. It's a big difference. A differentiable function is smooth and rounded that way. Whereas a function with a corner or a cusp is misbehaving differentially. No derivative there. No derivative there. No derivative there. No derivative there. This is not even a function. No derivative there. Anywhere you got that as abrupt change, you got no derivative. And you can't calculate it. Alright. So locally linear is what they're trying to show you there. And the rest you kind of have to do with graphing and pictures and all, right, on the back? Okay. All right, I'll leave you in peace. Again, what we tried to do today was the formula for the cube of a binomial. By the way, somebody remembered that. I'll leave it at, yeah.
Did you tell us the answer
Number 8? I'll cheat and work it out quick.